If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in the methods of impulse and momentum, we study very important idea, that is conservation of linear momentum. Till so far we have studied impulse momentum principle and its applications. Today talk will be based on understanding of conservation of linear momentum with the help of impulse momentum principle. And for that, we know that the momentum conservation is applicable for a system. So first we develop impulse momentum principle for a system, and with the help of that, we try to extract various ideas of conservation of linear momentum, and I'm sure that it will help you to understand the conservation of momentum in more greater detail. And again, just for simplicity, we keep on discussing very simple or elementary applications today. Such applications see here on this diagram. A man is stepping out of a boat. It's a very common experience that when someone steps out of a boat, the boat gets recoiled backward. This fact we can explain with the help of momentum conservation. As you know from your lower classes that if there is no external force on a system, its total linear momentum remains conserved, means it will not change with time. Here, if we ignore the resistive force from water, horizontal resistive force, so we can say there is no external force on the manned boat system in the horizontal direction. And before the man was stepping out of the boat, boat and man both were standstill, so their total linear momentum was zero. So when the man steps out of the boat, in this process there is no external force. So total momentum of the system still remains zero. But you can see the man is gaining a leftward momentum. So to make the momentum zero or to keep the momentum zero, the boat must gain a rightward momentum. So you can say the boat get recoiled. This idea we can also explain with great simplicity with the help of Newton's third law. What is that? When the man is stepping out, he pushes the boat by his feet backward. So the boat get recoiled, and reaction force of the boat on the man help the man to step out. Actually, here you can see that this idea we can explain with great simplicity with the help of Newton's third law. So then what is use of the conservation linear momentum? So we will not going in that thing that what is the use of this principle at present. First we try to understand the principle and we apply it in several problems. Later on we'll see how remarkable this idea is. And it is so remarkable that it is considered as one of the most enlightened principle of the classical as well as modern physics. So as I told you, first we discuss impulse momentum principle for a system of particles. For that purpose, we take the same example of system of particle what we have taken while developing work area theorem for a system of particles. So we consider a system of n particles of masses m1, m2, mi and mj and mn. They may be point masses or rigid bodies in translation motion. Here I will reiterate again that the notion of particle in mechanics means either a point mass or a rigid body in translation motion. So let us see on diagram here. You see the particle of mass m1, particle of mass m2, the particle of mass m3, mi, mj and mn. Here there are several forces. Few forces are shown by capital letters and few forces shown by small case letters. If you see the small case letters, they are this force. They are in between first particle and particle. This is what first particle and ith particle. This is what first particle and two particle 2 number. So they small case letter, the forces what I had represented, they are internal forces system. And this capital letter force F1 is the net external force for the system acting on particle M1. Similarly here, Fi vector capital is what? Net external force of the system acting on ith particle. So let us document these notations first. What are the internal forces? They represent by small case letters here. Small Fij vector, by definition what I am saying it, force on ith particle by jth particle. Similarly, what are external forces? Capital Fi, by definition I am denoting it net external force for the system on the ith particle. Here one more thing, all the forces we are not showing this diagram because the diagram will become too much complex. So what we have idea we are taking here, all the internal and external forces are not shown for better readability of the diagram. So diagram should remain clear. So we show only those forces in which we are interested. Again, there we take some other notations. Initial and final velocities of these particles at the instant t initial, ti, and t final respectively be denoted by, here for initial velocity we use symbol u, and for final velocity we use symbol v. So initial velocities u1 vector, u2 vector, ui vector, and un vector. So u1 vector is initial velocity of m1. Similarly, what is ui vector? Initial velocity of mi. And similarly, what is un vector? Initial velocity of mn, this particle. Similarly, final velocities will be v1 vector, v2 vector, vi vector, and vn vector. Now no need to explain them. Again we say what is impulse momentum principle for the particle mi. Actually, if you see in the previous class, we have developed impulse momentum principle for a isolated particle or single body. So we apply the same principle here. We can apply the principle now on a single particle. Say, let us choose the particle ith particle. So what we have to add impulses of all the forces acting on the ith particle, and sum of these impulses must be equal to change in momentum of the ith particle. So for ith particle, this external force for the system, this is also acting, and all these internal forces of the system are acting as external force on the ith particle. So their impulse we should also have to account for. So let us write integral ti to t final capital Fi dt. So this term represents impulse of the net external force of the system acting on mi. So let us write it. Impulse of the net external force for the system acting on mi. Now we add impulses of all these internal forces. For that we have to add say here summation j is equal to 1 to n and j is not equal to I, integral ti to t final small fij dt. Here this integral term is the impulse of this force fij, and ith we are choosing this equation for ith particle. So here to include all these forces we have to vary this j. So we vary j from 1 to n, but j is not equal to I because ith particle cannot apply force on itself. Now we have taken impulse of all the forces acting on mi. So what is this? Impulse of all the internal forces of the system acting on mi. Let us write it. Impulse of all the internal forces of the system on mi, and that will be equal to change in momentum of the ith particle. So what will be final momentum? mivi. What will be initial momentum? miui. So it will be mivi vector minus miui vector. So that is what equation of impulse momentum principle for ith particle. Now we can write such equation for all the particles and add them. So let us see here. This is change in momentum of the mi particle. So what we can proceed further. Now summing all the left hand members and all the right hand members of equations written for all n particles of the system, we obtain. So what we obtain? We add the first term I is equal to 1 to n integral ti to t final capital F dt. So what is this integral? It is impulse of external force on ith particle. Now if we change I is equal to 1 to n, so this entire term will represent impulse of all the external forces acting on the system. So let us write here net impulse of all the external forces on the system. Again now we add impulse of all the internal forces. So for that let us write here summation I is equal to 1 to n, and here summation j is equal to 1 to n, j is not equal to I, integral ti to t final vector fij dt. So you can see the term under bracket is impulse of all the internal forces of the system acting on ith particle. Now if you vary I is equal to 1 to n, so it will be what? Net impulse of all the internal forces of the system. So here net impulse of all the internal forces of the system. And this will be equal to what? First term will be summation I is equal to 1 to n mi vi vector. This will be final momentum, total final momentum of the system. So total final momentum of the system minus summation I is equal to 1 to n mi ui. This is total initial momentum of the system. Now just of course this equation we have written to understand the idea, but you can see these notations are too complex to use several times. So we just simplify the notations and try to understand each and every term. The first member of the LHS is the net impulse of all the external forces on the system. We denote it by summation j external, j vector. So for impulse we use the letter j. So this term we represent by summation j external. Similarly, this term we have to represent by summation j internal. Now the second member of the LHS is the net impulse of all the internal forces of the system. We denote it by summation j internal. But here we have to take one thing into account. What is that? Every internal force has its equal and opposite reaction on a body that is also included in the system. In addition, an action and its reaction exist simultaneously. Therefore, the net impulse of all the internal forces must be a null vector. So that is very important idea. Actually, in work energy theorem, we have seen that net work done by all the internal forces may or may not be zero. Actually, internal forces are equal and opposite, but while we are calculating their work, we can see that displacement of every particle may not be equal. They may be different, but when we are accounting for impulses, each internal force has an equal and opposite internal force in the system. Again, both the forces will act for the same time interval, so their impulses will cancel. So in the same way, for each pair of internal force, net impulse will be zero. That's why the total impulse of net internal force will be a null vector. So summation j internal total is a null vector. So that is very important idea. So when we are accounting impulse momentum principle, so what you take, we have to account impulse of only external force of the system, and this is what final momentum and this is what initial momentum. The first and the second member of the RHS are the final and initial momentum of the system. We denote them by summation pi and summation p final vector respectively. So now we can write very simple things. The impulse momentum principle for a system of particles now can be expressed as summation j external is equal to summation p final minus summation p initial, all are vectors. So that is very simple statement. So we get rid of this complex notations, and again I will mention that the total impulse of all the internal forces will always be a null vector. So what we say, what this principle states, that the total impulse of all the external forces on a system is equal to change in linear momentum of the system. So here the principle states the net impulse of all the external forces on a system of particles is equal to the change in linear momentum of the system. So that's a very simple idea. I'll again say that what is the impulse momentum principle for a system of particle, that is net impulse of all the external forces on the system is equal to change in momentum of the system. Now with the help of that, we try to understand principle of conservation of linear momentum. So principle of conservation of linear momentum, as I told you that this principle is a very fundamental principle of physics. So what you can say, the principle of conservation of linear momentum, or simply conservation of momentum, is one of the guiding principle of the classical as well as of the modern physics. It states that in absence of external forces or a net external force during a time interval, the total linear momentum of the system remains conserved in that time interval. So here there are two terms. in absence of axial forces or in net axial force. Of course, there may be several forces may be acting, but if their resultant is zero in a time interval, in that time interval, total linear momentum of the system remain conserved. And what we mean by term conserve means total linear momentum must not change with the time. It must be a constant. So we can write here fi vector is a null vector, or summation fi vector is a null vector. What this shows that every external force is zero. What it shows? Of course, there may be external forces, but their resultant is zero. Under these two conditions, whether this or that, total linear momentum will be conserved. And what we can write in mathematical equation, d of summation p vector is a null vector, or summation p vector is a constant. It shows that total linear momentum system will not change in time in the time interval in which this condition or this condition is fulfilled. Now we know that momentum is a vector quantity. So this equation can be written into its component. So we'll use here Cartesian component. And why we're using that? When you use x component, so at that time, or y component z time, at that time, we can avoid the vector notation. And we can use plus and minus sign to denote directions, because in x direction or x component, there will be only two directions, either in the positive x or in the negative x. Similarly for y and z. So to convert this equation into scalar notations, we resolve it into components. In Cartesian components, so what we can write? Summation Fix is zero. Means every external force x component is zero, or summation Fix is zero, or net external force in x direction is zero. In this case, what you can say, summation Px is a constant, means total x component of momentum will not change with time, or it will remain conserved. Similarly, we can write for y component. What is that? Summation Fiy is zero, means y component of force on every particle is zero, or there may be y component of forces on the system, but the resultant is zero. What you can say? Summation Fiy is zero. And now what we can write here? Summation Py is a constant. In the same way, we can write for z component. What? Summation Fiz is zero, or summation Fiz is zero. What it shows that summation Pz is a constant. So in this way, we can write this vector equation into three scalar equation. And of course, while using this principle, this method will be much more helpful. So linear momentum is a vector quantity. Therefore, in absence of external forces or a net external force in a particular direction, component of linear momentum in that direction remains conserved. So that is very important idea. Of course, total linear momentum of system may or may not be conserved, but if we can find a particular direction, if in that direction there is no external force or there is no net external force, component of momentum of that direction will remain conserved. So sometimes this may be very, very useful, as we have seen in the stepping out of boat example. At that time, we have seen the horizontal momentum was conserved. Special remarks. Now here comes what we can add to the understanding of conservation of momentum principle with the help of impulse momentum principle for a system. What we can say? Let us see. First point, if in presence of external forces, the net external impulse in one part of a time interval cancels that in another part of the time interval, the total linear momentum of the system will remain unchanged but not conserved. It is a very important idea. Here what we can see, we can divide the time interval concerned into say two parts or three parts. Say for example, we are taking two parts. If total impulse of all the external force in one part cancels the total impulse of all the external force in the second part, so for the time interval, total impulse is zero. And with the help of impulse momentum principle, what you can say, there must be no change in momentum. It means final momentum system must be equal to initial momentum, but in between momentum was changed. So it is not the conservation of linear momentum, but mathematically we can use it just like that, conservation of momentum while solving problems. So what we can write here, very important idea. Summation Pi is equal to summation P final. Means if total initial momentum is equal to total final momentum, it means it does not imply that momentum is necessarily conserved. Here, summation Pi may not be conserved, or may not be, because in between, from initial instant to final momentum, final instant, momentum may change. But what is that? Total impulse of the forces in the interval is zero, but between the interval it was not zero. So momentum was changed during the interval, but initial and final momentum is zero. So please take care of such situation. Here we cannot say that it is conservation of momentum. Now, second very important idea. This idea holds true for a particular direction also. Actually, that is not for a total momentum. We can use this idea for a particular direction also. Now, what was the second idea? For an impulsive event, if no external impulsive forces are present in a direction, component of momentum of the system in that direction can be assumed fairly conserved for all practical purposes. Now again rewrite, just I read this statement again because that is very important idea. For an impulsive event, if no external impulsive forces are present in a particular direction, the component of momentum of the system in that direction can be assumed fairly conserved for all practical purpose. That is what. Suppose we are considering an impulsive event, means an event of very, very small duration. If for that event, there is no impulsive external forces are present, but there are forces which are present, but they are finite. So by finite forces will not be impulsive. So they will change the momentum system, but very negligible amount. So strictly for such event, we cannot say the momentum is conserved. But what we can say, yes, momentum was changed, but the change we can neglect. So we can consider such event as examples of conservation of momentum. And this momentum conservation we apply fairly approximate, very fair approximation, and it is true for all practical purpose. Say for example, we can consider an explosion of a shell in air. So explosion process is of very small duration, but for that duration gravity was acting on the shell. But gravity is a finite force, so it is not an impulsive force. So because of gravity, total momentum of the shell during the explosion process has changed by so negligible amount that change we can neglect. So what we can say? We can assume the momentum shell to be fairly conserved, but not strictly conserved. So these are the two very important idea what we can understand only in the light of impulse momentum principle. Now we are ready to apply what we have learned to some example problems. Example 1. A shell moving with 50 meters per second in a free space explodes into two fragments of equal masses. After the explosion, one of the fragment moves with 50 meters per second backwards. What is the speed and direction of motion of the other fragment? Now we can solve this problem in two ways. One way I will discuss later, that is based on some intuitive understanding. Of course, that approach will feel better, but here this problem we can solve strictly by using the vector equation. So how we can proceed? Since the shell is in free space, no external forces is acting on it, therefore the linear momentum of the shell remains conserved. Here conserved means strictly conserved, denoting the mass of the shell by 2m and velocity before explosion by u vector. The principle of conservation of momentum, PCM, suggests us to write. Why I am assuming 2m? Because it is given that the shell has exploded into two fragments of equal masses. So we assume the masses of the fragment m and m. So mass of the shell will be 2m. So how we can write here? Summation Pi vector is equal to summation P final vector because of conservation of momentum. So what is initial momentum? 2mu vector is equal to minus mv vector plus mv vector. Why? That is this u vector we are assuming velocity of the shell. So one of the fragment moves with the same speed 50 and 50. So one fragment has speed u but in reverse direction. So its velocity will be minus u vector. So its momentum will be minus mv vector. And momentum of the second vector, we assume velocity v, so it will be mv vector, and v vector is unknown, so what we define. Now from this equation you can see very easily, you can cancel m and m and m, and so what we have, 2u vector is equal to minus u vector plus v vector, so v vector will be 3u vector, so we can write it very easily, v vector is equal to 3u vector. What it suggests? That velocity of the other fragment is thrice of the velocity of the first shell and in the same direction. Substituting the given value u is equal to 50 meter per second, what we get? V is 150 meter per second in the direction of u vector, because from here it is visible. Now I am coming on the second approach, intuitive approach, or in so many instances, in so many situations, the direction of velocities we can estimate, as in this case. Very often, direction of motion of bodies in an event can intuitively be estimated, as in this case. What we can see in this case, suppose a shell before the explosion was moving towards right. So one of the fragment will move towards left, backward. So other fragment must move towards right just to satisfy conservation of momentum. And in this way, we can represent momenta of the different bodies in diagram. As one fragment moves in reverse direction, the other must move in the forward direction to satisfy principle of conservation of momentum. Thus, we can draw this diagram or following diagram. What is that? We assume the shell of mass 2m moving with velocity u, say in this direction. After the explosion, one of the fragments, say this explosion, this fragment will start moving in the backward direction, so its velocity will be u, so its momentum will represent here mu, and direction shown here. Now just momentum is conserved, say there must be no other momentum in the other direction, so this fragment must move in that direction just to satisfy the momentum conservation. So we assume mv in this direction. Now from this diagram we can write very easily what we can have x and y component, but there is no need to write y component equation. We write only x component of equation. So summation pix is equal to summation p final x. So what we can say, 2mu is equal to minus mu plus mv. So here the direction towards right we are assuming positive, and towards left we are assuming negative. And by solving this equation you can easily get that v is equal to 3u. Here sign of v is coming positive, so what direction we have assumed for v is the same. Now what we can predict from here, it is recommended to follow as far as possible this intuitive understanding based approach. Of course, in situation where you are not in a position to estimate direction of motion of different bodies, we can proceed with that kind of vector approach. But in situation where you are able to estimate direction or decide direction, in those situations, drawing this momentum diagram and writing equation will be much more interactive. Example 2. A shell fired from the ground with a velocity u at an angle theta to hit a target on the ground at a distance r from the point of firing, but the shell explodes into two identical fragments at the highest point of its trajectory. If one of the fragment falls vertically downwards, where will the other fragment hit the ground? Here see, very important thing, one of the fragment falls vertically, it falls, it is not given that one of the fragments start moving downward. So falls means it starts with zero velocity. It means immediately after the explosion, one of the fragment has zero velocity. And one more thing, the explosion has occurred at the highest point. So at the highest point we know the velocity of shell is horizontal. So total momentum must be horizontal. And one of the fragment has zero momentum. So momentum of the other fragment must be in the same direction as momentum of the shell was. That was intuitive based approach, and with the help of that we draw the diagram and write a conservation of momentum equation. But one more thing, whether the momentum is conserved or not, as a convention, if it is not mentioned about air resistance, we ignore the air resistance, or we assume air resistance to be absent. So in absence of resistance, what we can say, there is no horizontal force on the shell. Of course there was force of gravity. So if we consider the force of gravity, what we can say, during the explosion, total momentum of shell was not conserved. Strictly it was not conserved, but the duration of explosion is infinitely small. It is an impulsive event, and for that duration, gravity being finite, its impulse will be negligible, so it can change the momentum by infinitely small amount. So even in that case, what we can say, total momentum of the shell is almost conserved, or we can say we can assume it to be conserved practically. Now if we suppose air resistance, so in horizontal direction, air resistance will be a finite force. So again, what impulse momentum principle suggests, during the explosion, impulse of air resistance will be of negligible amount, so its effect on the total momentum will be negligible, so we can assume the momentum to be conserved for all practical purpose. But here air resistance was not mentioned, so what we assume, there is no resistance, so we assume air resistance absent, so momentum horizontal component to be strictly conserved. But whatever cases, we have to write conservation of momentum equation. So what the idea is, since there is no external horizontal force on the system or shell, the horizontal component of momentum of the shell remains conserved. So what we can proceed further, denoting mass of the shell by 2m, momenta of the shell immediately before the explosion, and that of the fragments immediately after the explosion are shown here in the diagram. Now why we are assuming 2m? Because it is given the shell has exploded into two identical fragments. So at the highest point, the velocity of shell was horizontal. So what you can write here, 2m ux, and here ux is the x component of this velocity, here assuming x to be horizontal direction. So that was momentum of the shell immediately before explosion. And what will happen immediately after explosion? One of the fragment has zero velocity, so it has no momentum. So other fragment must have momentum in this direction. So from here, what we can write, x y component, so no need to write equation y component, only x component. So summation p I x vector is equal to summation p final x vector. Here this equation we can write in vector form as well as in scalar form, but equation we write in scalar form, so no need to write vector notation. So rightward direction we take positive, leftward is negative, so there is no momentum in this left direction, so no need to use anywhere negative sign. So 2mvux is equal to mvx. So from here, what you can write here, Vx is equal to 2ux. So velocity of this fragment has become double of the velocity of the shell. Now we can think idea of projectile motion, that air time or time of flight is decided by the vertical component of velocity. Now you can see, to reach from the point of firing to the highest point, projectile take half of their time. Again, to reach from the highest point to the time ground, projectile take next half of the air time. Why? Because at the highest point it has no vertical velocity, so it has just if you consider the vertical component motion, it has zero velocity, so it must take the same time has taken to rise to the highest point. So here let us think about since explosion occurs at the highest point and velocity of the fragment remain horizontal, it will take half of the air time to hit the ground. That is very remarkable idea. So what we can think here, this was trajectory of the shell if explosion were not there, but at this point explosion has taken place in this way. So this fragment will straight fall down, and this fragment has acquired velocity 2ux. So it will not hit here, it will hit at somewhat further, because if it has velocity ux, it will hit here, but it will hit further here. But where it will hit, we have to find that one. Here we can see that vector u and its horizontal component we are representing by ux, so we have mentioned it earlier, and it was vertical component. Now range is what? Ux into t, t is the air time. So we represent r by ux into t. Now what you can see, this distance from here to here, from this highest point to this horizontal distance. So it will be this velocity into half of their time. So 2ux into t by 2. So it will be again uxt. So this will be equal to r. You can see from here. Now you know that this distance is half uxt, r by 2. So what is this distance? Again r by 2. So we can write it half ux into t. So it is r by 2 or 0.5 r. So PQ is equal to half ux into t or half into r or 0.5 r. So what we can say from here? The second fragment hits the ground at a distance 0.5 r ahead of the target. So again you can see to solve this problem we have taken that intuition based approach, because here we are in a position to estimate directions. So wherever we are in a position to estimate direction, instead of using vector equation, try to use this approach. One more thing about conservation of momentum. Of course, when the explosion took place, force of gravity was there and force of resistance was there. So under this condition, what you can say? Momentum of the shell was not strictly conserved. It was fairly conserved because gravity and air resistance both are being finite forces. Their impulses during negligibly small time interval of the explosion will be negligible, so they can affect the momentum total by negligible amount. But momentum has been changed, but changed by negligible amount, so we can use conservation of momentum for all practical purpose. One more thing, if in a problem air resistance is not mentioned, so we assume air resistance to be absent. In this condition, what we can say? There is no horizontal force, so horizontal component of momentum will remain conserved. So what the idea we have taken, but we have to understand each and every idea in very minute detail. Example 3. A shell fired vertically upwards explodes at the highest point into 3 fragments A, B and C of masses MA is equal to 4 kg, MB is equal to 2 kg and MC is equal to 3 kg respectively. Immediately after the explosion, the fragments A and B acquire velocities. VA is equal to 3 meter per second in the positive y direction and VB is equal to 4.5 meter per second in the positive x direction as shown here in this diagram. Situation is given. So immediately after explosion, the velocity are shown. This fragment A, which has mass 4 kg, has velocity 3 meter per second in the positive y direction. And fragment B, which has mass 2 kg, has velocity 4.5 meter per second in the positive direction. And we have to estimate velocity of fragment C. Part A, find velocity VC vector of the fragment C. So we have to find velocity of fragment C in vector form. Now we here components are given, so use or this coordinate system is given, so we use the same coordinate system. Solution. What we can think? The shell was fired vertically upward, explodes at the highest point into 3 fragments. It is not given whether this shell is explosion takes place in free space or not, but for safety we assume explosion to take place in the gravity. Again gravity, and even if we consider air resistance, both the forces are being finite, so their impulses during the explosion will be negligible. So total momentum of the shell will remain fairly conserved. Of course, here the total momentum is not strictly conserved, but again, change in momentum we can neglect. So we use here conservation of momentum as an approximate idea. So the explosion takes a negligible duration. Therefore, the only external force of gravity, being finite in magnitude, acts as a non-impulsive force. Its impulse can be neglected and momentum of the shell can be assumed fairly conserved for all practical purpose. What do you mean by all practical purpose? Even if you consider gravity, the velocity of shell will change, so fragment will change by so negligible amount that even when they will hit the target. So again here the air resistance was not mentioned, and it is a convention that if there is no mentioning of air resistance, always assume it to be absent. The fragment fly off and acquire the given velocities due to internal forces developed during the explosion. So what we can say, momentum of the shell before the explosion and that of fragments after the explosion are shown here in diagram. So here we can multiply these velocities by masses, so we can show the momentum. But before the explosion, momentum was zero because it explodes at the highest point. So at the highest point, its speed was momentarily zero. So at that moment, momentum is zero. Now about fragments, we can say x, y, z, all the direction. So this momentum of piece A will be 12 because its velocity is 3 and mass is 4. So momentum is 12 kg meter per second. Similarly for fragment B, mass is 2 kg and velocity is 4.5. So 2 into 4 is 9. So it's 9 kg meter per second. And momentum of fragment C we can write here, mvc vector. Now what we use? The vector equation. So applying the principle of conservation of momentum PCN, what suggests? P initial vector is equal to P final vector. So here we have a null vector is equal to MA VA vector plus MB VB vector plus MC VC vector. Now we substitute the values, and before substituting value we can write here what is VC. So VC vector is equal to minus of MA VA vector plus MB VB vector upon MC. So here just there is typing mistake, it will be MB. So now we substitute the value and get the answer. So what will be VC vector is minus 3i cap plus 4j cap meter per second. So in this way we have found the velocity of fragment C. Now what is the second part? Find kinetic energy released in the explosion. How much kinetic energy has been released? Actually, immediately before the explosion, shell was at rest, so it has no kinetic energy. So now what we can say, total kinetic energy of fragments came out of explosion. So after explosion, if you sum up all the kinetic energy of the fragments, we can say it is kinetic energy released during the explosion. So what we can see, the explosion occurs at the highest point where shell was momentarily at rest. In addition, during the negligible duration of the explosion, the work done by gravity, being vanishingly small, should be neglected. It means that is very important idea, because in this impulse event there is no external forces are acting. It means work done by all the external forces is zero. So only what forces are doing work? Internal forces, the forces generated by explosion, because in explosion some gunpowder is burned and gases ejected by the burning gunpowder will push the fragments apart. So this is internal force. The fragment fly off and acquire the given velocities due to forces of expanding gases produced in the explosion. These forces are internal forces of the system. Thus, the total kinetic energy acquired by all the three fragments is the kinetic energy released in the explosion. So here in the diagram, these are velocities of fragment A 3 meter per second, fragment B 4.5 meter per second, and fragment C 3i cap plus 4j cap. Now we can write total kinetic energy of these fragments. Thus, the total kinetic energy release is the total kinetic energy of this system immediately after the explosion. So what we can write here? Summation K is equal to Ka plus Kb plus Kc. So what is K? That is half into Ma into Va square plus half into Mb into Vb square plus half into MC into Vc square. Now by substituting values we can find, that is half into 4 into 3 square plus half into 2 into 4.5 square plus half into 3 into 3 square plus 4 square, and by using this what we get, 18, that is 20.25 and 37.5. So the total current release is 75.75 joule. So in this way, we have taken this example. Now let us proceed for the next example. Example 4. A man of mass m jumps from a plank of mass capital M. Before the jump, the plank was sliding with a constant velocity v0 towards the right on a frictionless horizontal floor. That was situation. The man is jumping from the platform, and before the jump, the velocity of the platform as well as the man is v0 towards the right. Part A. If the horizontal component of velocity of the man after the jump is u with respect to the ground, find velocities of the plank after the jump. So what is given here? Just immediately after the jump, velocity of the man with respect to ground is u. So, and again, horizontal component of velocity. Of course, the man is jumping, it will have some vertical component as well as some horizontal component. So what is given? If the horizontal component of velocity of the man with respect to ground is u, we have to find what is velocity of the plank after the jump. So here what we can think, no horizontal forces act on the system of plank and the man. Thus, total horizontal component of the momentum of the system remains conserved. Actually, you can see there is no horizontal component. Actually, force of gravity is acting on the man, force of gravity is acting on the plank, and there is normal action on the plank, and there is no friction from the floor. So there is no horizontal actional force. So total horizontal component of momentum will remain conserved. Denoting velocity of the plank after the jump by v, we can represent the momenta of the bodies before and after the jump as shown here in the diagram. So that is before jump, what momenta? mv0, that is the momentum of the plank, and here small mv0, momentum of the man, because man was moving with the plank, and that was a, we can say the momenta of both the bodies. And immediately after jump, we can assume velocity of plank v and in the same direction. So this is the momentum of the plank, and horizontal component of momentum of the man will be what? mu, because velocity u is given with respect to ground. Now we are concerned here with the horizontal component only, so we are not showing the vertical component of momentum of the man. Now from here, by using conservation of momentum, what we can write? Very simple idea, that is this momentum plus this momentum is equal to this momentum plus this momentum. Let us see. Applying PCM for the horizontal component of the total momentum, we get summation Pix is equal to summation P final x. So what is summation Pix? mv0 plus small mv0 is equal to capital MV plus small mu. And we have to find this v, and we can easily find v is equal to capital M plus small m v0 minus mu upon capital M. You can verify the solution. Now this was very simple idea. Let us see the B part. If the horizontal component of velocity of the man after the jump is u with respect to the plank, find the velocity of the plank after the jump. Here in this part, what is given? Horizontal component of velocity of the man after the jump is with respect to plank. So what we do? So let us see here. Similar to the previous part, no horizontal forces act on the system of plank and the man. Thus, total horizontal component of the momentum of the system remains conserved. It means, again, as we have seen in the previous part, that is, there is no horizontal force on the system. So total horizontal component of the system will remain conserved. What is system? Man and plank. Initial momentum of the system with respect to the ground is known. Thus, use of frame attached with the ground is recommended. Again, initial momentum was with respect to ground, so we have to use frame with respect to ground. One more thing, that is here, of course, velocity of the man was given with respect to plank, but during the jump, the plank was acquiring an acceleration because of push of that. So here the plank will be a non-inertial frame. So here we have to use inertial frame, so we use a ground frame. Denoting velocity of the plank after the jump by V towards the right, the horizontal component of velocity of the man with respect to the ground is, here we use a relative motion idea. What? V man vector is equal to V man with respect to Planck vector plus Vp vector. Again, we are writing for horizontal component only. So what we have? Vmx is equal to Vmpx plus Vpx. Here, horizontal component or x component of velocity of the man. Here, x component of velocity of man with respect to Planck. Here, x component of velocity of Planck. Now, what is that? This Vmx, that is it is u that is given, the horizontal component of velocity of man with respect to Planck, and horizontal component of velocity of Planck after the jump, because it is with respect to velocity of Planck after the jump, so we are assuming it to be v, so here it is v. So horizontal component of velocity of man with respect to ground is u plus v. Now we can show the momentum. The horizontal component of momentum of the bodies before and after the jump are as shown here in figure. That is before the jump. So this momentum is mv vector, capital. It is small mv naught this way. And now after the jump, the Planck has velocity v. So its momentum, we suppose here mv, its momentum is mu plus v. That is after the jump. Now what we can further say, that is conservation momentum we can write for horizontal direction. Applying PCM for the horizontal component of the total momentum, we get what? Summation Pix is equal to summation P final x. So initial was capital MV naught plus small mv naught. And final is capital MV plus small mu plus v. Now by solving this, what we will find? V is equal to V naught minus mu upon m plus small m. So in this way we can solve this problem. Now we have seen this very important idea, because whenever such kind of situation is given, we have to take that velocity of bodies are given with respect to what? Generally in this problem, both kind of situation may be given. Velocity of the man after a jump with respect to ground, and velocity of the man after a jump with respect to Planck. So how we can solve these two situations we have seen in this example. Now let's discuss the next example. Example 5. A block of mass m is held compressing a spring with the help of a light thread on a frictionless L-shaped plank of mass capital M. The setup rests on a frictionless horizontal floor. After the thread is cut, the block leaves the spring with a velocity u relative to the plank. So situation is given here, that is an L-shaped plank, and here is a block. The block is held compressing the spring with the help of this light thread. The mass of thread is negligible. What do you find? Find recoil velocity of the plank. So first you find what is recoil velocity of the plank. Means when the thread is cut, the block will rush toward this side, and because of spring force, the plank will go in this side. So it is called recoil velocity. What is the idea here? Due to absence of external horizontal forces on the block plank system, the horizontal component of momentum of the system remains conserved. Actually, on the block and plank system, there is no horizontal external force, so horizontal component of momentum here will remain conserved. Initial momentum of the system with respect to ground is known, a null vector. Basically here it is null vector. Thus use of a frame attached with the ground is recommended, denoting velocity of the plank after the jump by v. Towards the left, the horizontal component of velocity of the block with respect to the ground is given again by relative motion idea. Here we use jump, means we can say the block is just like a jump. So again we use the same idea as we are earlier. So VB vector is equal to VB with respect to Planck vector plus V Planck vector. Now use this equation for x component, means horizontal component only. So what is Vbx is equal to Vb with respect to Planck x component plus V Planck x component. Now we substitute the values. What is given and what we assume. What we assume here, velocity of the Planck after the block jump here is V towards the left. So we assume it towards the left in this way. So how we put the values? So this way to find. So this is a U because velocity of the block with respect to Planck will be towards right. So plus U and it will be minus U. So we are taken in minus U. So velocity of the block with respect to ground x component, horizontal component is U minus V. Now we draw the momentum diagram. The horizontal component of momentum of the bodies before and after the thread is cut are shown here. So how we can see? Initially, before the thread was cut, there was no body was moving, so total momentum will be 0. So we assume here no momentum. Now we put equal to sign. Now we show the momentum of both the bodies with respect to ground. So thread is cut, you can see thread is cut and the block has leave the spring. So its velocity will be what is we have assumed V towards left. So its momentum Planck will be here capital MV towards left and block will be small m into this velocity U minus V. So it will be small m into U minus V. Now what we can write applying conservation momentum, that is we can have x and y component. So no need to write equation y component, only x component. Applying PCM for the horizontal component of the total momentum, we get what Pix is equal to summation P final x. So that is a result from the conservation momentum. So what is initial momentum? 0. What is final momentum? Minus capital MV plus small m U minus V. So let us put the values. 0 is equal to minus capital MV plus m into U minus V, and by solving this we can find V. V is mu upon m plus m. So in this way we have found velocity of the Planck recoil velocity immediately after the thread is cut. Now let us see what is the B part. Find the elastic potential energy released by the spring when, of course, the thread is cut. So these Planck and the block both will acquire some kinetic energy. From where this kinetic energy came? This kinetic energy came because of the spring. So here we can say that is this total kinetic energy will be equal to potential energy which was stored in the spring which has been released. So we have to calculate basically the total kinetic energy of the system after the thread is cut. So how we can think? Result obtained in the previous part, what? This V and U minus V. And what is V? V was equal to mu upon m plus m, and because U was given only. External forces acting on the system are the forces of gravity on the block and on the Planck, and the force of normal reaction from the floor. None of these forces do work. Therefore, total work done by external forces is 0. What we can say here, of course there are external forces, but their total work is 0 because gravity on the Planck, gravity on the block and normal reaction. The displacement of particle on which these forces are acting are perpendicular to these forces. So none of these forces are doing work. So their total work done will be 0. Now, the internal forces in the system are the spring forces and the forces of normal reaction between the block and the Planck. Here, this normal reaction. Among these forces, only the spring force do work. Therefore, why? Their internal force, you can say the spring force are internal force, and the normal reaction between the Planck and the block is internal force. But this normal reaction is not doing work because you can see displacements of Planck and the block are perpendicular to these normal reaction. So only spring force is doing work. So what you can say, summation W internal is equal to work done by spring. And now we can apply work energy theorem for a system of particle. Initial kinetic energy of the system is 0 and the final kinetic energy can be calculated with the help of the velocities acquired after the thread is cut, because we know that this velocity and both the velocities we know, and we can find, that is kinetic energy, both the kinetic energies. Applying work energy theorem on the block Planck system, what you can write? Summation W external plus summation W internal is equal to summation K final minus summation K initial. And we know that this term is 0 and this term is equal to work done by spring. So we substitute the values. 0 plus work done by spring is equal to K final. What is K final? Half m into v square plus half into small m into u minus v square. And what is K initial? It was 0. Please take care of this, because velocity of the block with respect to ground is u minus v. Now we solve this equation, and it is not very difficult, simple algebraic manipulation. So what we have, work done by spring is equal to half mv square plus half m u minus v square. So we are omitting the 0. And now for the solution, what we can take? For this we have to substitute value of v here. And by substituting value of v, what we get? Work done by spring is equal to half m upon m plus m into u square. And you can verify this answer. Again, this expression will have great importance, and that importance we'll discuss after studying center mass, and when we discuss about a reference frame attached with center mass, and we call it center mass frame. In center mass frame, you'll see this relation will have very, very great importance. Again, at that time, this term m into m upon m plus m for a two particle system, this term we call as reduced mass. But let us take a discussion of that thing there. Now we come on the next example. This work done by the spring force is equal to the elastic potential energy released by the spring. And we have seen it earlier. And for next example, what we can see? Example 6. What is that? A small block of mass m is placed on a plank of mass capital N that rests on a frictionless horizontal floor. The block is given an initial velocity v vector by a sharp hit. Due to friction between the block and the plank, sliding between them ceases after a finite time interval. So situation is given here. The plank is placed on a frictionless horizontal floor and block is placed on plank, and the block is given a velocity v0 by a sharp hit. But there is friction between the block and plank, and what is given? After some time, finite time, the slipping between block and plank will stop. So what we can say? After that, or from that instant, block and plank will move with the same velocity. So what is asked here? Part A, find the final velocity v of the block. So we have to find first final velocity, and for that we can use conservation of momentum. Of course, here we can use Newton's law also, because by Newton's law we can calculate acceleration of plank as well as acceleration of the block. And now use equation of constant acceleration of motion. Suppose acceleration of plank, and you can see very easy, that will be mu z backward. And acceleration of what is plank, which will be mu mg upon capital M forward. And what you can say, v0 minus mu g into t is velocity of the block. And what is velocity of plank? Mu mg upon capital M into t. When these two velocities will be equal, equate these expressions, what you will find? T. And by substituting t in any of the velocity equation, you can find velocity of the block as well as that of plank. But you can see how much time consuming this process is. But here the final velocity we can find very easily by using conservation of momentum as well. How? That is initial momentum, we know, mv0, and final momentum will be what? Small m plus capital M into what is the final velocity, because finally both the bodies are moving with the same velocity. Say that velocity is v, so we can write straightforwardly mv0 is equal to m plus capital M into v. So what is v? mv0 upon m plus capital M. Now let us write the solution. Due to absence of external forces in horizontal direction on the block Planck system, the horizontal component of momentum of the system remains conserved. So what we can write? Denoting the final velocity of the block and the plank by v final. Initial momentum immediately after the hit and final momentum after the sliding between the block and plank ceases are shown. Here, initial momentum immediately after the hit. So after the hit, you can see. Of course, during the hit, there is friction between the block and plank, and that is acting on the plank, but this friction is finite and duration of hit is infinitely small. So during that time, the block will acquire a velocity which can be neglected for all practical purpose. So we can say velocity of the plank immediately after hit is 0. So what we can write here, that is the momentum immediately after the hit. So only the block has acquired any appreciable velocity and the velocity of plank is negligible. So it assuming it is 0. So that is momentum. And after the hit, after the slipping ceases, both are moving with the same velocity v final and v final. So these are the momenta. So by conservation of momentum, what we can write? We can have to conserve momentum only in x direction. So what we can say? Applying the principle of conservation of x component of linear momentum, we get summation pix is equal to summation p final x. Here, initial x component momentum totals of the system and total final x component momentum system. So initial was mv naught, final is what? Mv final plus capital Mv final, from where we can find v final is simply mv naught upon m plus n. So that was very simple idea. Now let us see what you have to calculate in the B part. Find the total work performed by the frictional forces in this process. Actually, such kind of problems we have done in work energy theorem. At that time, we have used Newton's law and work energy theorem. But now how we can simplify the idea. Let us see here. Forces of gravity on the block and on the plank, and the force of normal reaction from the floor on the plank are the external forces on the block plank system, and force of kinetic friction on the block and on the plank are the internal forces in the system. And of course, there is a normal action between block and plank, so that is also an internal force. So here, what you can see, this and this and this friction. Here we are not showing that a normal action between block and plank. Of course, it's internal force, and its work will be 0 on individual body, because for that normal action, displacement the block is normal, and for this normal action, displacement plank is also normal. So no need to show this. Only we consider all these external forces. Again, these external forces are doing no work, because displacement of the bodies on which these forces are acting are perpendicular to these forces. So only this force of kinetic friction is doing work. Now we use, again, similar to previous problem, application of work energy theorem on the entire system. So what you can see, none of the external forces do work, as displacements of the particles on which they act are perpendicular to the respective forces. Force of kinetic friction does negative work on the block and the positive work on the plank, resulting in a total negative work. How? Actually, force of kinetic friction will act opposite to displacement of the block, so it will do negative work. Again, force of kinetic friction on the plank will is in the direction of displacement, so it will do positive work. But how I can say, or how we can say the total work done will be negative? Because we get friction, total work done will always be negative. Total work done, because it will always, of course, I'm talking about kinetic friction. It will always result in loss of mechanical energy. So what we can take here, W external is equal to 0, and W internal summation total is what? Work done by frictional force, total work done by frictional force. Now we put these values in work energy theorem, but before, let us see the kinetic energies. The total kinetic energy final will be what? Velocity final we have calculated. So it will be half capital M plus small m into V final square. So and we substitute the value of V final. In this way, we can calculate the final kinetic energy. And what is the initial kinetic energy? That is only of the blocks. That is what? half small m into v naught square. But let us proceed for that. Since initial and final velocities and hence the initial and final kinetic energies of the system are known, therefore we can use the work energy theorem on the block-Planck system to find the total work done by the frictional forces, that is the internal forces. So how we can see initial and final kinetic energy, let us calculate. Here we have to learn something. There is let us see what we have to learn. Initial kinetic energy, no need any explanation. K block initial plus K Planck initial, so that is half m into v naught square, that is, and it is 0, so it is half m v naught square. Summation K final is equal to KB final plus KP final, B for block, P for Planck, so it will be half small m into v final square plus half capital M into v final square, and from here half and v final square we can take common, so what we can write here, half small m plus capital M into v final square. Now substituting value of v final, we can find the final kinetic energy. So what is v final? We know that is mv naught upon m plus capital M. If we substitute it here, what we get? M square v naught square upon twice of m plus capital M. So that is what. Now I have mentioned you here we have to learn something. What is that idea? We can see that kinetic energy for a body, for a particle, is momentum square upon twice of mass. At final instant, both the bodies, block and Planck, are moving with the same velocity, so we can assume them as a single particle. So what we can write here? That is momentum square upon twice of total mass. And we know the momentum is conserved. And there is no need to write final momentum. Let us see initial momentum. What is initial momentum? mv naught. So we can directly write it. How? Summation K final can also be calculated as K final is equal to summation P final square upon twice of total mass, or summation P initial square upon twice of total mass, because momentum is conserved. And why we can use this? Because final moment, at final moment both the bodies are moving same velocity, so we can assume them as single particle. So use this expression, and if you use this idea you can write it directly. What? m square v naught square upon twice of m plus m. So if you are able to use this idea, you can save this much of time. Now we substitute these values in work energy theorem for the system and find total work done by frictional forces. So what you can take here, now substituting the values of total work done by the external forces, that is 0, total work done by the internal forces, that is equal to work done by friction, initial and final kinetic energies of the system in the work energy theorem for the system, we get what the theorem is. Summation W external plus summation W internal is equal to summation K final minus summation K initial. So let us substitute the values. So that was 0. It is work done by friction. What is final kinetic energy? M square V naught square upon twice of M plus M minus half M V naught square. Now by solving this, what we get? Summation of W friction is minus half M plus M upon M into M upon M plus M into V naught square. Now we can see the similar expression what we get earlier. But again, its importance we discuss while this will discuss use of center mass reference frame. But what we can make the idea here, that is relation between kinetic energy and momentum of a particle, that is K is equal to P square by 2m. Actually, whenever you get a chance to use the relation to write kinetic energy, use it, because in this way you can save time, and we have seen earlier, and that was the thing what I mentioned you, we have to learn something to write kinetic energy final. And again I see how we can use this relation finally for final kinetic energy, because finally block and Planck are moving with the same velocity, so we can assume them as single particle, and mass of that is m plus m. Again momentum is conserved, so final momentum was equal to initial momentum, so we can write initial momentum square upon twice of mass. So this way we can simplify our idea. Now let us discuss the next example. Example 7. A bullet hits and pierces a block that is placed On a horizontal floor, there is friction between the block and the floor. Neglect loss of mass of the block as the bullet pierces through it. So this situation is given here on this floor. The block is placed and there is friction between the block and the floor, and this bullet hits the block and pierces, make a hole and comes out of the block from other side. Again, due to the hole, what is the loss of mass of the block, that we have to neglect. And what we have to calculate? Can you apply momentum conservation during the piercing of the block by the bullet? Actually, during the piercing process on the bullet block system, we know there is frictional force in horizontal direction. Of course, in vertical direction, there are forces, gravity and normal direction. But here in the horizontal direction, there is friction. Even in presence of friction, can we apply conservation principle? Yes, we can apply. Because this friction force has finite magnitude. And process and duration of this piercing process is negligible. So during that negligible time, impulse of this friction force will be negligible. So it can change momentum by negligible amount. So we can assume momentum to be fairly conserved. Now this idea, when momentum is fairly conserved in some impulse event, that idea we can only understand by applying impulse momentum principle. That's why I have correlated here conservation of linear momentum with impulse momentum. And of course, we have developed the idea from the impulse momentum principle. Now let us proceed what the logics are here. External forces on the bullet block system are their weights, normal reaction, and force of kinetic friction on the block from the ground. So these are the external forces: the weight of bullet plus weight of the block plus normal reaction of the ground and this friction. So what you can see, vertical component of the momentum. What can we say about vertical component? During piercing of the block, weight of the bullet and the block are counterbalanced by the normal reaction from the floor or from the ground. So what you can see, thus a zero net external force makes the vertical component of momentum of the system conserved. But what we can say about horizontal component? Horizontal component of momentum, and that is a very important idea. Again, I have explained you earlier. Let us see. In the horizontal direction, the only external force on the bullet block system is the frictional force or friction from the ground. Finite magnitude of this force in the vanishingly small duration of the piercing process allows it to be considered as a non-impulsive force. Why not impulsive? Because its impulse can be neglected. So what you can see, thus the horizontal component of momentum of the bullet block system can be assumed fairly conserved. Means it is not extremely conserved, but if you make it is conserved, assume it conserved, what calculation will make? They will be almost the same as actual condition, because the values will be so, what values you obtain, they will be so differ from the actual value that they cannot be measured by any equipment. So that's why we can say fairly conserved, and the previous problem, what I have said, fairly conserved for all practical purpose. Now see what is meaning of practical purpose. The mass of the bullet is m is equal to 50 gram. The bullet hits the block horizontally with a velocity of ub is equal to 600 meter per second. Mass of the block is m is equal to 1 kg. The bullet emerges out of the block with a velocity vb is equal to 400 meter per second, and coefficient of friction between the block and the floor is mu is equal to 0.25. These information are given. Now these values are given and we have to calculate something. What? Find velocity of the block immediately after the bullet emerges out of it. So that was situation. Just the moment when bullet is emerging out of the block, at that moment we have to find how much velocity the block has acquired. And we know that for this process, we can assume the momentum of the bullet and block to be conserved for all practical purpose. So we use conservation of momentum idea, denoting velocity of the block when the bullet emerges out of it by UB, capital B, momentum of the bullet and the block immediately before the bullet hits the block and immediately after the bullet emerges out of the block are shown here in diagram. We show the all momentum. So that is initial, the block was red, so momentum of bullet is what? Small m u into small b. Just see here, we are using small b, and for block we are using capital B. That is momentum immediately before bullet hits the block. And what is immediately after the bullet emerges out? We assumed velocity of the block to be u into capital B and velocity of bullet to be v into small b. So this momentum will what? M into u subscript capital B and small m into v into subscript small b. So that is the moment of this bodies immediately after the bullet emerges out of the block. Now we use that's a coordinate system, so no need to go in y directions, only we consider x direction. So horizontal momentum we assume practically conserved. Applying principle of conservation of momentum for horizontal component, we get summation pix is equal to summation p final x. So what is summation pix? Small mvb. What is summation p final x? This momentum plus this momentum. So let us write this. Mub is equal to mvb small plus capital M u capital B. From here we can calculate u capital B. That is very simple. What? Small m ub minus vb upon capital M. So in this way we have expression for velocity of the block immediately after the bullet emerges out of it. Now substituting values, we can find this velocity. Substituting the given values, we get ub is equal to, that is what is a 0.05 kg, 600 minus that is velocity, how much is 400 upon mass 1 kg. So what you get? ub is equal to 10 meter per second. So block has acquired a velocity of 10 meter per second because of the piercing process. Part C, find the distance slid by the block before it stops. And now you can see for this purpose we have to use work energy theorem, because now we know the velocity of the block immediately after the bullet has emerges out. Now in further moment there is no interaction between block and bullet, and final velocity of block is 0, and we have to find space interval over which this velocity is changing. So that is area of use of work energy theorem. Distance slid by the block consists of two portions, that are the distance slid during the piercing process and the distance slid after the piercing process. The first part becomes negligible due to finite velocity of the block during the vanishingly small duration of the piercing process. To determine the second part of the distance, the work energy theorem should be used. Here the idea what I conveyed to you is very important, because when block is acquiring a velocity of 10 meters per second, that process, the piercing process, is very small duration process. So you can see vanishingly small duration, and during this process the block velocity has varied from 0 to v, so it has finite velocity always. So having finite velocity in negligible small time, what is displacement? 0. So in that piercing process time, the distance, of course the block has slid some distance, but that distance is negligible, so we neglect it. So we have to consider which distance? Just distance slid by the block after piercing process, and for that we use work energy theorem. So that was situation is given: initial kinetic energy, final kinetic energy, and all the forces, and you can see from here only this friction is doing work. And initial kinetic energy, we can write what the velocity we have obtained, u capital B, and value was 10 and mass is 1, so you can write this value. So initial and final kinetic energies of the block. What is the initial? Half into capital M into u capital B square. Let us substitute values. Half, that is u capital B we know, and we substitute the value here, And in this way you can find this. Now, how we are writing here? One thing, you can use this idea, or other thing, you can use this idea. What? Suppose if a second part was given, was asked directly, so you can write this expression straightforwardly. What? By using momentum conservation. What is loss in momentum in the bullet is gain in momentum of the block. So you can see m into ub minus vb is the loss in momentum of the bullet. So that will be gain in momentum of the block. So that is momentum, and momentum is square up by twice of mass. So this you can write directly also. But here, of course, we have calculated UB, so you can use this relation. So you can either of these, and by how we can written here p square by 2m, just because of that. So this relation will help you to speed up your process. And of course, if A and B part were not asked and only C part were asked, so you can write this expression very directly. But we have calculated here UB, so you can find kinetic energy. What is K final? 0, and that we know. Work done by the forces acting on the block are work done by gravity is 0, work done by normal reaction is 0, and work done by friction is minus mu capital mg into x, distance xb, this way. Now we substitute all these things into work energy theorem. Substituting these expressions in the work energy theorem, we get W initial to final is equal to K final minus K initial, and now substitute values, that is work done by gravity Wg plus Wn plus W friction is equal to K final minus K initial. So substituting the expressions, 0 plus 0 minus mu mgxp is equal to 0 minus m ub square minus vb square upon twice of mass. So from here we can find what is xb, m square ub minus vb whole square upon 2 mu m square g. Now this expression has importance because if the part C was asked directly, so we have done this way. Otherwise you can substitute find kinetic energy initial from here and this, and substituting values you can find the answer very easily also. Substituting the given values, we get xb is equal to 20 meters. So that you can verify. Now let us come on the next example. Example 8. A wooden block of mass capital M is suspended with the help of 2 threads to prevent rotation while swinging. A bullet of mass small m hits the block with the horizontal velocity v0 and get embedded. If the bullet block system swings to a height h, deduce suitable expression for the speed of the block, or sorry, speed of the bullet. Actually this situation is given here. This block is suspended by 2 threads. Why 2 threads? Because when it swings it will not rotate. Actually this idea and this setup is called ballistic pendulum, and this experiment is used to find velocity of bullets. But that's why what we can measure, when bullet will hit, it will swing to height, and when it will swing to height we can measure how much height it will swing, and with the help of this height we can calculate velocity of the bullet, and that is asked. Let us see how we will calculate. The bullet hits the block and get embedded. As a result, the bullet block system acquires a horizontal velocity, say u, in a negligible small time interval without any appreciable displacement. Actually, the process during which the bullet is piercing it and getting embedded, in that small time interval, the block will not acquire any appreciable displacement because it will acquire a finite velocity, but time duration negligible, so displacement block will be negligible, so the height raised by the block will be negligible. So we can neglect that process, the height risen by the block during that time. Total momentum of the bullet block system remains conserved. Why it remains conserved? Actually, you can see while the bullet is being embedded in the block, in that negligible time, the block has acquired a final velocity. but time is negligible, so block will have negligible displacement. Because of that negligible displacement, the thread will be tilted by negligible amount angle. So whatever tensile forces the thread will have, those tensile forces will have negligible component in the horizontal direction. Again, these negligible component of tension in negligible time interval will provide almost zero impulse. So we can say momentum system remains conserved. Actually here tension components are not finite. So we'll not say the momentum is practically conserved. Here momentum is conserved. We draw the diagram and show the momentum before the bullet hits the block and momentum after the bullet is being embedded. Now we write momentum conservation equation. So Pix is equal to P final x. What is Pix? mv naught. What is P final x? M plus m into u. Again, we are not interested in u, we are interested in v naught. So u will substitute in terms of height risen. And for that, what you use? Work energy. Because initial velocity of the bullet block is u and final velocity is 0 and there is displacement. So change in speed over a displacement is area of work energy theorem. So we use here work energy theorem. So what we can do? The maximum height to which the bullet block system swings can be easily obtained with the help of the work energy theorem. How? Initial and the final kinetic energies of the bullet block system. Now we can write what is final kinetic energy? 0. And for initial kinetic energy, there is no need to write u. Again, bullet and block are moving as a single object, so we can use p square by 2m. And momentum is conserved, so there is no need to write this equation. Only we can use initial momentum upon square upon twice of total mass. So you can see here k is equal to p square by 2m. So what is initial kinetic energy? K initial mv naught square upon twice of m plus m. So here you can see the advantage of this. No need to write momentum conservation equation. Only we know this momentum will be equal to this momentum. So kinetic energy we can write. What is final kinetic energy? 0. Now we written expressions for kinetic energy of the bullet block system, initial and final. And the task remaining is to see the forces and their work on this body. For this, we see the situation how the bullet block system, now we not call it system, we call it single object. Now how the block is moving and how the forces are acting on it. So initial velocity is u. So it will swing to a height h. This and here its velocity becomes 0. Now see the situation at some intermediate state here. Now this intermediate state forces acting are gravity and tensile forces of thread. Let's show the tensile forces. Now you can see these tension forces are always perpendicular to the path or displacement. So they will not do any work. Only external force what? Weight of block plus weight of bullet will do work, and that we can write simply what? The gravity is acting downward, displacement is upward, so work done will negative what? Minus m plus capital M g into h. During the swing, the tensile forces in the string and force of gravity on the bullet system are the external forces. And how we can calculate their work? Only external forces of gravity on the system does work. Work done by tensile forces is 0 as displacements of these particles on which they act is perpendicular to the forces. It will always perpendicular. So work done by tension will be 0. So only work done by gravity will have to consider as external. But let us see internal force. Actually, bullet and block are moving as single objects, so there is no need to consider their internal forces. The bullet and the block constitute a rigid body, so there is no need to consider work done by their internal forces. They will not do any work. Total work done. So what we can see? Work done by various forces. Work done by external force is equal to minus m plus m into gh, that is, and work done by internal force, that is 0. Now we can substitute these values in work energy theorem. Substituting the expressions for kinetic energies and work in the work energy theorem. we get summation W external plus summation W internal is equal to summation K final minus summation K initial. So what it will be? Minus M plus MGH plus 0 is equal to 0 minus MV naught square upon twice M plus M. And by solving this, you can find V naught is equal to M plus M upon M under root 2GH. Today in this lecture, we have studied momentum conservation, its application on very elementary examples. In the next lecture, we discuss application of conservation of momentum principle in some advanced level problems. And that will be somewhat more interesting to understand. Thanks for patient listening. We'll meet in the next class. The words of language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.